In this video, we're going to learn how to write the equation of a plane in 3 space. In order to do that, a plane is determined by a point and a vector that is normal to the plane. So let's take a second. If we think back to the equation of a line, we define that with a point and a direction vector, which was a vector parallel to the line. And now for the equation of a plane, we're defining it using a point and a vector that's now normal to the plane. Now what does normal mean? That means perpendicular or orthogonal. Okay. Or we can define the equation of a plane with 3 points or variations based off of that. Okay, so if we know 3 points on the plane, we will also be able to write the equation of it. And really there's a whole list of different situations that we'll be able to write the equation of the plane for instance, 2 vectors on the plane. And that comes from knowing 3 points. 3 points, we can create 2 vectors. 2 vectors, we will be able to write the equation of a plane, right? Maybe an equation of a line and a point. So the way they present the information to us will change from problem to problem, but we need to isolate the information we need based on what's given, and then we can use that information to write the equation of a plane. And ultimately that information is a point and a vector that is normal to the plane. Now this vector is called the normal vector and is denoted with an n. Okay, so there are 3 ways that we write the equation of a plane, and we'll build through all 3 of them. If we look at our diagram, we have our plane, P naught as 2 points. I'll put points for each of these. And we are going to use this to write our equations. So the first thing, let's visualize what that normal vector is. So if we draw a vector that is perpendicular to the plane, that is the normal vector. And remember, vectors are not fixed in space, so that normal vector could be drawn anywhere on the plane. It could be even drawn in the opposite direction, as long as it's perpendicular to the plane. Now, we have 2 points on the plane defined. P naught is a fixed point, a point we know. Okay, so we'll define that as x naught, y naught, z naught. That is the point we know. And now point P we're using to represent a general point on the plane. Okay, so we'll define that as x, y, z. If we can create a vector on the plane, knowing that the normal vector is perpendicular to the plane, the vector on the plane dotted with the normal vector will be 0 because the angle between those 2 vectors would be a right angle. They would be orthogonal vectors. So our goal is to create a vector on the plane so that we can dot it with the normal vector. Now, knowing 2 points, we can create a vector between the 2 points. So we can create a vector from P naught to P. Okay, and underneath, let's just define some pieces. So n is the normal vector. Let's give it some components that will be useful when we write the equations out. So we'll call that capital A, B, C, since we use lowercase ABC for our line video. And this vector that we just defined between P naught and P, so terminal minus initial, so x minus x naught, y minus y naught, z minus z naught. Now, just to emphasize, point P is a general point on the plane. P naught we know, that might be the point 1, 2, 3. P is representing some general point, any point on the plane, because any vector that we draw on the plane will be perpendicular to the normal vector. So we want the ability to generalize vectors on the plane, which is what this lets us do. That x minus x naught, y minus y naught, z minus z naught. Okay, so using the dot product to build the equation of the plane, if we take the normal vector and we dot it with that vector that we created, P naught P, Well, those vectors are orthogonal. They're perpendicular to one another, so the dot product is 0. Now, how did we define that vector? We did vector subtraction. We took p minus p naught. Now, we didn't visualize it, but we can easily, right? If we go from the origin to vector p and to vector p naught, and we want to define the purple vector, which is that p naught p. I'll write that in. That's p naught p. Negate p naught's vector so that we have correct vector addition. Initial point, terminal, initial, terminal. And that would give us p minus p naught. And that's nice because we can distribute out the dot product. And that would say that n dot with p is equal to n dot p naught. So another way to think of this is if we take the normal vector and dot it with vector p, we should get the same thing as dotting the normal vector with vector p naught. This is great to get an intuitive sense of writing the equation of a plane, but for practical purposes, it's not going to be easy for us to use. So that's where the other two forms of the equation of a plane come in. So for the scalar equation of the plane, if we take this first expression of n dot p naught p and replace it with these vectors that we've written underneath our diagram, so a, b, c, dotted with x minus x naught, y minus y naught, z minus z naught, that will be equal to 0. Right? They are vectors that are orthogonal to one another. And if we do the dot product out, we have a times x minus x naught plus b, y minus y naught plus c, z minus z naught equals 0. So this is the scalar equation of the plane. And then the general equation of the plane, if we clean up our scalar equation, so we distribute the a, the b, and the c, we'll have ax plus by plus cz on the left side, and then moving those terms over, we'd have ax naught plus by naught plus cz naught. And for practical purposes and to create a clean general equation, we're going to group all those together and call them D. So ax plus by plus cz equals D. And typically, this is the equation of the plane that we look to write, which is the most simplified version of the equations that are above. So we do that dot product out, we clean it up, simplify it, there's our equation of the plane. It's important to notice that the coefficients a, b, and c, those coefficients of x, y, and z give you the components of the normal vector. And when you pick up on that, it can save us a bit of work and effort when we are writing the equation of a plane, or if we're given an equation of a plane and we need to pull out that normal vector, right? So the coefficients of x, y, and z are the components of the normal vector. You might want to make a note for yourself that could be helpful. Okay, so find the equation of the plane through the point 1, negative 4, 3 with normal vector 2i plus 3j minus k. Okay, so we're going to take a general point in the plane and create a vector with the fixed point we know, right? So we know 1, negative 4, 3. We'll use the general point x, y, z. Okay, so our normal vector 2, 3, negative 1. Right, that's our normal vector, dot with p naught p, which in this case is x minus 1, y plus 4, z minus 3 equals 0. So doing the dot product out, we have 2 times x minus 1 plus 3 times y plus 4 minus 1 times z minus 3 equals 0. So 2x minus 2 plus 3y plus 12 minus z plus 3 equals 0. 2x plus 3y minus z equals 10, 13, negative 13. And there is our equation of the plane with a normal vector of 2i plus 3j minus k through the point 1, negative 4, 3. Next example, find the equation of the plane that passes through the points 2, 1, 2, 3, negative 2, 4, and negative 1, negative 3, 1. So this is our example that starts with 3 points. Now, we still have our same goal. We need a normal vector and a point to be able to define the equation of the plane. So if we call these points A, B, C, we can find 2 vectors between the 3 points. So let's say we find vector AB. So B is the terminal point minus the initial point. So 1, negative 3, 2. And then we'll define vector AC. So C is now the terminal point. So negative 3, negative 4, negative 1. Our normal vector is going to be the cross product of AB and AC. So I, J, K, 1, negative 3, 2, negative 3, negative 4, negative 1. So now's a good moment to pause, practice your cross product, and then pick up the video. Okay, so if you did that, whether you use cofactor expansion or your diagonal method, we should find, so 3 minus negative 8, so plus 8, so 11i, and then negative 1, and plus 6, so that's 5, but j is negative, so minus 5j, and then k, negative 4, and then minus 9, so negative 13k. So there's our normal vector. Point, well, we have 3 of them. We can pick any point we want. So let's say we pick that point. So we'll go directly into our scalar form. So 11 times x minus 2 minus 5 times y minus 1 minus 13 times z minus 2 equals 0. Again, getting comfortable with that fact of the components of the normal vector being the coefficients when we expand out the dot product. So then 11x minus 22 minus 5y plus 5 minus 13z plus 26 equals 0. So 11x minus 5y minus 13z equals, so let's see, negative 22, 26, that's 4, 5 is 9, so negative 9, we move it to the other side. Other option we have here is we can jump directly here, 11x minus 5y minus 13z, and the way to find the constant would be plugging in one of the 3 points. If we plugged in point A, point B, or point C, that's how we could figure out this constant here. Right? So we have a few different ways into the problem. Ultimately, we get the same answer, and that's what's most important. Find the equation of the plane that contains the lines x equals 3 minus 2t, y equals t plus 1, and z equals t plus 7, and x equals 3t, y equals 1 minus t, and z equals t plus 1. All right, so we have 2 different lines. They're both in the plane, and we need to write the equation of that plane. So we have our same goal. We need a point and a normal vector. Right? So if we just draw out a little picture to help ourselves. So basically they're saying, okay, here's one line. Here's another line. Okay, important that the lines aren't parallel, because then when we go to take a cross product, we would get the 0 vector. Right? So we're going to want to check that as we go. So can we take information off of the lines to find the information we need, which is a point and a normal vector? So let's start with a point. Since both of these lines are on the plane, a point on either one of the lines would be sufficient. Could we find the point of intersection? Of course. That would take a bit more work, but it would be correct. Let's just more simply pick an easy point. So if I look at the second line, if I make t equals 0, then the point would be 0, 1, 1. Okay, so there's one of the points on the line. Now we need to find a normal vector, which means we need a cross product somewhere. Well, the equations of the lines tell us points and tell us direction vectors. Right, so there's, let's say, direction vector 1 on the blue line and direction vector 2 on the green. So algebraically, if we look, direction vector 1 would be negative 2, 1, 1. Direction vector 2 would be 3, negative 1, 1. The normal vector then will be the cross product of our two direction vectors. So set it up, I, j, k, negative 2, 1, 1, 3, negative 1, 1, and pause the video, finish the problem out all the way through the equation, and then play and see how you did. Okay, so looking at my work here, the normal vector is 2, 5, negative 1. So using that last method I talked about, so 2x plus 5y minus z equals, if we were to plug in the point 0, 1, 1, we'd get 0 plus 5 minus 1, so that's equal to 4. And we can check that by grabbing a point, so let's say a point on the first line, so 3, 1, 7. All right, if we plug 3, 1, 7 in, this should work. So 3, 6, 1, so 11, minus 7 is 4. All right, so that means a point on the other line does work in the equation of our plane. All right, so we're incorporating cross products, still using vectors and points to define the equation of the plane. Now we can sketch a plane, and typically what we're going to look to do when we sketch a plane is draw the portion that's in the first octant. Right? We don't really worry ourselves about trying to represent the whole plane, since it is infinite and it would be challenging to do. So if we find our intercepts, right, so our x-intercept, where y and z would be 0, so that would be 2, 0, 0. Our y-intercept would be 0, 6, 0. Our z-intercept would be 0, 0, 3. So marking out our coordinate system, 4, 5, 6, 1, 2, 3, 4, 5, 6. Try to make them even, 1, 2, 3, 4, 5, 6. Okay, so we have 2, 0, 0, 0, 6, 0, and 0, 0, 3. Connect the intercepts in a little triangular portion of the plane. Okay, so this is the portion of the plane 3x plus y plus 2z equals 6 that is in the first octant. And then extends out infinitely if we wanted the actual full plane. Okay, so we've written the equation of the plane, being given a few different pieces of information. Now let's talk about two planes and comparing how they can interact with one another. So two planes can either be parallel or intersecting in 3 space. Okay, so these are more like lines in 2 space. So we either have two planes that are parallel or the same, or that intersect. And the intersection of two planes will form a line. Right? Think of the room around you. If you look at the wall and the ceiling, right, look where they intersect, and you would be able to draw a line at that intersection. So describe the relationship between the planes 5x plus 3y minus 4z equals 19 and negative 10x minus 6y plus 8z equals 5. All right, so the normal vector of the first plane is 5, 3, negative 4. Normal vector of the second plane is negative 10, negative 6, 8. If we compare the two normal vectors, we should notice that the second normal vector is negative 2 times the first normal vector. So they are scalar multiples. And when the normal vectors are scalar multiples, that means that the normal vectors are parallel. So parallel normal vectors tell us that we have parallel planes. Right? Now, if we have planes that are not parallel, then they often ask us to write the equation of the line of intersection. So find parametric equations for the line of intersection between the planes x minus 2y plus z equals 0 and 2x plus 3y minus 2z equals 3. So if we remember to write the equation of a line, we need a point and a direction vector. So let's try to visualize this first. So we have two planes that intersect. So I'll make a horizontal plane and a vertical plane. Okay, so their intersection would be right here. There's our line. Now we need a point that's on both of these planes. I wish there was a simple way, but we really just have to think about a solution. Because we have two equations with three variables, there is no system that we can create. So if we look, the point 1, 1, 1 would work here, and the point 1, 1, 1 would work in the second plane. Now, I do have the advantage that I've looked at this problem before. Some of these examples, the point will come easily. Some you will have to work a little bit harder to find. But stick to zeros and ones to start. Usually some combination of zeros and ones should give you a point that works in both equations. So now that we have the point, we have to figure out how we're going to find the direction vector. Well, planes give us normal vectors. So the first plane gives me normal vector 1, which I'll define, right? That's the coefficients of our x, y, and z. So 1, negative 2, 1. And the second plane gives us what I'll label as n2. So the second normal vector, 2, 3, negative 2. So how are we going to create some vector that's parallel to the line? Well, if I move the vector, because vectors aren't fixed, that direction vector, if I put it right there, that looks like the cross product of the two normal vectors. So if we cross n1 and n2, we will get the direction vector. And then once we have the direction vector, we can easily write the equation of the lines. Okay, so I, j, k. Notice we're doing quite a number of cross products in this video, since cross products give us vectors that are orthogonal to the two vectors we start with, and that's one of the pieces we look for in writing the equation of a plane. Right, so doing out this cross product quickly, 4 minus 3 is 1, negative 2 minus 2 is negative 4, but j is negative, so positive 4, and then 3 plus 4 would be 7. So we have our direction vector now. We have our point. So our equations will be x equals 1 plus t, y equals 1 plus 4t, and z equals 1 plus 7t. Right, so there's our set of parametric equations that represent this line of intersection. Now the last thing we have to define is the angle between two vectors. So not vectors, two planes. So if two planes are not parallel, then we can find the equation of the line of intersection, like we just did, and the angle between them. If the planes are not perpendicular, I know it got cut off there, so that's the word not perpendicular, the angle between the two planes is defined as the acute angle between their normal vectors. Okay? If you think about how two planes intersect, there will be an acute angle and an obtuse angle. So when they're asking, we're looking for the acute angle, which just means we need to make sure that we're finding the inverse cosine, typically, of a positive value. Okay, so find the angle between the planes. So that's really just the angle between their normal vectors. So the first normal vector is 1, negative 2, 1. The second normal vector is 2, 3, negative 2. And to find the angle between vectors, that's dot product. So n1 dotted with n2 equals magnitude of n1, magnitude of n2, cosine of theta, theta being that angle we are looking for. So dot product is 2 minus 6 minus 2 magnitude of n1, so let's see, magnitude of n1, square root of 1 plus 4 plus 1, so square root of 6. Magnitude of n2, square root of 4 plus 9 plus 4, so square root of 17. So square root of 6 times the square root of 17, cosine of theta. So negative 6 divided by square root of 6 square root of 17 equals cosine theta. But remember, we're looking for the acute angle. So we do want to take the absolute value of that dot product. So that means that theta, which is the acute angle we're looking for, is the inverse cosine of 6 over square root of 6 square root of 17. And we'll leave it as an exact angle. Okay, so equation of a plane defined from a point and a normal vector. They could give us information in a whole bunch of different ways. That's the information that we need to pull out. Then we looked at how planes can interact with one another, being parallel or intersecting. We defined the equation of the line of intersection, and we also defined the angle, the acute angle, between the two planes.